Welcome back to part 2 of this video. The last video we did parts A and B, so this video will finish off this question and doing parts C and D. But before we get started, I would like to make a quick little correction for all of them, so for part A and B more specifically. Despite that we already have the solution, I never specified what n was, and so that's very important because this will actually make or break the actual solution. So for the first part, we said sine square root of lambda of x is equal to phase of x, where the square root of lambda, it's supposed to be the square root of n, is equal to n pi over L. And I need to be specific that n is an integer such that it's greater than 0, because it's every positive lambda value, and they have to be integers because that's where the sine function is equal to 0. And then same thing goes here for part B, and another way you can write this is where n is equal to 1, 2, 3, dot, dot, dot. So yeah, that's pretty much it that needed to be added to the answers. This becomes very important because for the sine function, every n pi is equal to 0 where n is an integer. So if it's not an integer, then it is possible that it won't be equal to 0. But now that we got that out of the way, let's actually finish the video. So for part C, it asks us to find the solutions with the condition of phase prime of 0 is equal to 0, and then phase of L is equal to 0. So plugging in our phase of 0, what we end up getting is phase prime of 0, my bad, is terrible line. So what we end up getting is the square root of negative lambda times a multiplied by hyperbolic sine of 0 plus the square root of negative lambda b times hyperbolic cosine of 0. This one should be just b, and this one square root of lambda a times, negative, sine of 0 plus square root of lambda b times cosine of 0. And so this is for the lambda is negative, lambda is 0, and lambda is positive. And so what this gives us now is pretty much just b's. Ignoring the constants here, and this is equal to 0. So this tells us that b is equal to 0. So again, it's not the end of the world because we still have a, and that's where our second condition comes into play. So phase of L now, this would be equal to a times hyperbolic cosine of the square root of negative lambda times L for the negative values of lambda. This one would just be a for lambda is equal to 0. And then this one would be a times cosine of the square root of lambda times L for lambda is positive. Now again, we want this to be equal to 0. So in order for this to happen, we can start finding what lambda is equal to. So for the first one was the same case as the last example for part B. We want hyperbolic cosine of the square root of negative lambda times L to be equal to 0, but this can never be equal to 0, making us to put a equal to 0, giving us a trivial solution. So that one won't work. Same thing goes with when lambda is equal to 0. That won't work because not lambda, a is equal to 0. So our last case is when this is equal to 0. So for this to be true, we want cosine of the square root of lambda times L to be equal to 0. And that will only be true when our lambda of n is equal to n minus 1/2 times pi all over L, and take that whole quantity and square it. So this does give us a non-trivial solution, making, I almost forgot again, where n is a set of integers such that n is greater than 0. And so our solution will be phis of x is going to be equal to cosine of the square root of lambda of n times x, where lambda, or not where lambda, where the square root of lambda of n is equal to n minus 1/2 times pi all over L, where n is an integer such that n is greater than 0. I'm pretty sure you noticed I got rid of the a, and that's mostly because it's a constant, so I can just make a equal to 1 and then just multiply anything by what it needs to respectively. But for the most part, this is how the general solution is. I'm just negating the constants. So now for our last part, part D, it asks us to find when both phis of 0, or phis prime of 0, and phis prime of L is equal to 0. So let me actually do this one. So for phis prime of 0, we can look at the previous example, part C, that this gives us b equal to 0. So b will be equal to 0. So equal to 0. So this forces us for b to be equal to 0. Cool. So we got that out of the way. So now for the phis prime of L. Phis prime of L will give us, it is going to give us the square root of negative lambda times a hyperbolic sine of the square root of negative lambda times L. Then this will give us 0, and then this will give us the square root of lambda times a times sine of negative times the square root of lambda times L. And we want this to be equal to 0. So for this one, for this to be equal to 0, well, this makes the square root of negative lambda times L to be 0, making us to conclude that the square root of lambda is equal to 0. But for this condition, the square root of lambda is negative, so this forces us for a to be equal to 0. So the first solution is not going to work. Again, because this is strictly when lambda is negative, but our lambda has to be equal to 0. So there's no solution. The second one, however, this is already true. 0 is already equal to 0. So that's a valid solution. So we know that lambda equal to 0 is a solution. So the last one, let's see what we get. So for this equal to 0, we want sine of the square root of lambda times L to be equal to 0. And the only way that's true is if the square root of lambda times L is equal to n pi, or thus giving us infinite solutions of lambda of n equaling to n pi over L quantity squared, where obviously n is positive integers. And so this case, it gives us two solutions. So our phis of x will be equal to some constant that we're just going to call a when lambda is equal to 0, and then cosine of the square root of lambda sub n times x, where lambda is greater than 0. And this is, well, lambda of n. And this is where lambda of n is equal to, or the square root of lambda of n is equal to n pi over L, such that n are positive integers. And that is pretty much it for this example. That's pretty much it for this video. Thank you so much for watching, and I'll see you in the next video.